Welcome back, everyone. So this is the final talk for today's morning session by Manoj Yadav. So I must say that Manoj is the big brother of Indo-Russian collaboration, because as far as I remember, the first Indo-Russian project that Valeriy and Andrei were part of, that was coordinated from the Indian side by Manoj. So it's a great pleasure to have him here.
Professor Pasi.
Professor Pasi, okay, that was Professor Pasi. Okay, so let's have his talk on Skew Braces. But you are part of that project, right?
Yes, I will mention that. Thank you, Krishnendu, for the introduction, and I thank the organizers for giving me this opportunity. So I wish my heartiest wishes to Valeriy and Andrei on them getting 60 years. And this is a milestone they have achieved, but I hope they will achieve many more milestones and our friendship will go forever. And so my association with Valeriy and Andrei goes back to 2009, when both of them visited HRI to participate in a conference. It was called International Conference of Mathematics in HRI. So HRI ICM, this was in March 2009. Then I visited them in the same year later, I think sometimes in June or July. And I was a part of that Indo-Russian project. In the Indian side, it was headed by either Professor Pasi or Gurmit Bakshi. And on the Russian side, I think it was Roman Mikhailov. And so I suppose this is the true story. And anyway, so let me start with some pictures which I took in 2009. This is Andrei in Sobolev Institute. We were working on class preserving automorphisms of unit triangular groups. And the next one is Valeriy and the bank of the river. And please notice that there is similarities because both of them are doing mathematics. So the Andrei is holding a chalk, but Valeriy is holding smoke. So there are sticks in their hands and they are doing mathematics. So this is the way I think this shows their the characteristics. So someone is very serious, works with the chalks, and other one is the seriously doing mathematics while smoke in his hand. So.
Can you send me a picture?
Sorry?
Can you send me a photo?
Yeah, I will send you.
Okay, thank you.
Yeah. All right. So now I come to the title of the booklet, and I had a look at this title and found that I am interested today talking about this corner, the upper right corner of this picture. And you have written this third Reidemeister move, the braided relation. And so my talk will be mostly around this corner of this picture. And these are the references which I will not mention afterwards, but the mathematics which I am going to present comes from these references. So this presentation is taken from these 5 references, mostly from these 5 references. All right. So I right away start from that top corner, top right corner of the picture, that braided relation is here. And so we define it on a set. So X be a non-empty set, and then a bijective map S from X square to X square. And this pair XS is said to be a braided set if this relation, the braided relation, holds in the domain of all maps from X cubed to X cubed. And the meaning of S1, 2, and 2, 3 is here. So when you want to apply S1, 2, then just apply S on the first two components, fixing the third one. And when you want to apply S2, 3, then fix the first component and apply S in the second and third component. So please have another look at it, because I will not show you this picture again. So whenever I say my pair XS is a braided set, I simply mean that X is a set, S is a bijective map, and this relation is satisfied. And so if you write this function, this map, as the component in the form of the components denoted by gxy and fyx. And so these functions, gx and fy, they are maps from x to x. And so the interesting things happen when these maps are bijections. So let us give a name to it. The pair XS is said to be non-degenerate if Gx and Fy are bijections to all X and Y. This resembles with the definitions in linear algebra. And so we call this set involutive if S square is identity. S is an involution in some sense. So we have said three things about this set X and the bijective map S. So if it satisfies braided relation, we call it a braided set. If the non-degeneracy is satisfied, then we call it non-degenerate. And when S square is identity, we call it involutive. So mostly in my talk, I will be talking about non-degenerate braided sets. So involutive will come a couple of times, but then I will mention it. So whenever I don't say anything, then assume that I'm talking about non-degenerate braided sets. All right. So in the abstract, actually, I said that I will first talk about the skew braces and then point out a connection with the solutions. But I have decided to do it in the reverse order. So first I will show the connection and then I will talk about the skew braces. So the connection, so what do I mean by a connection? So you start with a braided set, which is sometimes called a set solution of the braided relation. But in this talk, I will mostly avoid saying solution. I will mostly say braided set. And if you have a set solution, then if you compose it with a flip map, xy going to yx, then you really get a set solution of the quantum Yang-Boxer equation, and which I think most of you know about all the stories, so I will not repeat it here. So I will just say braided sets. And so how to associate something called skew brace with a solution. So I'm going to explain that now. So start with a braided set and write the bijective map as a component map. So Gx and Fy comes into picture. Then you can define a group which I denote by G sub x as the group generated by x modulo the relations given by the bijective map S. So xy is equal to gxy fyx. So if you want to see it as a free presentation of the group, then you take a free group on X and then take the normal closure of the subgroup generated by these relations and factor that out. So that is this group. You can also define another group, which this group is called a structure group. The structure group of the braided set. can also define a derived structure group of a braided set as follows, not by AX, A sub X. So here again generated by the set X, and the relations are given in this fashion. So actually these relations come from when you apply S square, then these double suffixes come into the picture, and it is taken from there. So this looks a bit complicated, but this is not so.
So when you apply S square, so are you assuming involutory?
No. So here I have said, because my side is just here, is I have explicitly said braided set.
So when you apply square,
even non-degeneracy is also not assumed in this definition.
so when you apply square, what are you equating it to get these equations?
No, I'm not equating anything. I only said that these terms, which looks a little complicated, they come from. So if you apply it second time, then you will see these kind of expressions. So the whole idea is that if you take your set to be involutive, then this term will actually become y. So involutivity will give you this is equal to y. So f(ix) dot y. So please notice that I have put different operations here, because in this group I have taken an operation which I'm not mentioning, and this is going to be different group. So the operation I have taken the dot. So when S is involutive, so then this will be y. So f(ix) y, and then y f(ix), because so I think I am making a little mistake here. I need to take it non-degenerate to say that. So okay. So anyway, so in this case we don't use non-degenerate, but when we want to define it for the involutive ones, then we suddenly will need non-degenerate. I will mention that. So my whole point was that this AX will actually become the free abelian group on X. So that will come here. So if X this set is involutive, then we can really say that AX is equal to ZX, the free abelian group. And in this case, actually, we also need it to be non-degenerate. So the non-degenerate involutive braided set, then this AX will be ZX. And this is the object of the study of the first reference, Ittinghoff, Sadler, Soloviev. They only studied involutive ones, and so they took this is called symmetric sets, which were involutive symmetric sets. So the braided non-degenerate and involutive. So I will put some example, the easy one. So if you just take the flip map, then this gives a braided set, and in this particular case, actually, not only AX, but GX also becomes ZX, the free abelian group on X. And there are certainly many more examples. I have not given them here because I'm really going to give you a host of examples when I define skew braces and the make constructions. So, and so although in general, when you take a braided set, it is very difficult to compute the structure group GX. In the simplest case, we notice that this is just going to be ZX. But in general, we don't know. But the striking property here is that, okay, we don't know about the structure group, but we can always find bijection between the structure group and this free abelian group. Not only this is a bijection, this is a one cocycle. So in this case, we can call it a derivation because ZX is abelian, but we will be using the terminology one cocycle because we will also have it in the non-abelian set. So I'm not going to show you this correspondence. I will show you a general version of this in generality. So that's what I explained here. So that bijection, we are really going to get a bijection between Gx and Ax, which is actually a cocycle. So I will, in next couple of slides, I will explain this.
So what is the action? I mean, when you are saying cocycle,
Yeah, I'm going to explain the action.
okay, okay.
Yes. So a non-degenerate braided set, I'm setting the scene here again, G, X, Y, F, Y, X. So the X going to Fx. You notice that Fx and Gx, because it's non-degenerate, so Fx and Gx are permutations on X. So this X going to Fx will really give a right action of Gx on X, and X going to Gx will give you a left action of Gx on X. So you can make this right action the left action by putting the inverse. So X going to Fx inverse really give it left action. So we really have two left actions of Gx on X, which really come from these component maps. So we let us denote them by star. Star is the left action which comes from Fx inverse, and circle is the one which comes from G. So really get these two actions. And then our setting is so, one really need to make some calculations to see this, that this star extends to an automorphism of the. So, I mean, this one really does not require any checking, because from the generators, the bijection on the generators of a free group really extends to an automorphism. So this one does not require any checking, but the next one, when we say that this is an action, and then this really extends to an action of Gx on Ax. So this one needs to make some calculations. It's not straightforward. So this is the action of Gx on Ax, which is induced by the star action. And so now take the semi-direct product of Gx and Ax, and here is the composition. The composition is given by this. And so I hope, Mahendra ji, I answered your question. And
Yeah, sure. Please go ahead.
thank you. So now define, natural map from X to Gx, and this A should be X. So psi A from X to Ax. In general, these are not injections, so they're just maps. And so then you can define a map from X to the semi-direct product by using these natural maps, psi Z and psi A, in this manner. And so then this map actually extends to a group homomorphism. Again, one really need to make some calculations to show this. S bar Gx to the semi-direct product Gx by Ax. And then if you define a map pi from Gx to Ax by, first go to this and then apply the projection on the second component. So this really comes very, very natural. So the definition is so nice, but it is not easy to prove that this is actually a bijection. So there's a theorem which comes from the paper, the third reference, which I have shown. So Soloviev, the non-unitary set theoretic solutions of the quantum Young-Buxley equation in 2000. So he actually, the main thing is to construct the reverse map and then prove that they are the inverse of each other. So this really involves lots of hard work, proving that pi is a bijective one cocycle. But good thing is that suddenly there is one. And so, and then you can define a subgroup of Gx by using these the kernels of these two. So it is a simultaneous kernels of these actions. And then it comes out that gamma is a normal subgroup of Gx. And also if you apply pi onto it, then you really get into Ax, and that is also normal. So the image is normal in Ax. And then the next result says that this pi induces a bijective one cocycle on the cosines. So that's one. And whenever X is finite, then these quotients are going to be finite. All right, so given a set X, we have defined bijective uncocycles from Gx to Ax as well as on the quotients. And then I'm now going to tell you that we can define something interesting, which we now call skew brace. So Ax dot is a group, and there is a bijection from Gx to Ax. So we transport the group operation of Gx onto Ax through pi, via pi. And so let me denote this direct sum is just a notation, because I have already used circle and dot. So that this is nothing to do with the direct product, it's just a notation. So transport the operation of Gx on Ax and then check this. So B dot C, this is a dot in original group Ax with dot, and the circle is the operation which is transported from Gx. And one can check that this condition is satisfied for all A, B, C in Ax as a set. And so this is called a right skew brace or skew right brace. So this is the definition. So I will make it more formal in the next slide. So starting from a non-degenerate braided set, you get an algebraic structure with two operations which satisfy this compatibility condition between the two operations, which is called a skew right brace. All right, let us make it now. So I will be working with the skew left braces. So let me just make a formal definition. So this definition was actually given by Coronary and Vendram in 2017. So algebraic structure G with two operations, dot and circle, is said to be a skew left brace if these two are groups, and this condition holds. So this is the distributivity, the kind of semi-distributivity is taken on the left. So this holds. And I have mentioned again some trivial examples. For example, take any group and take the circle is equal to that same operation of the group, then it is going to be a skew brace, actually trivial skew brace. So another example, which is a little more serious than the trivial one, is the opposite. You can define circle as the opposite of the given operation. And this brace actually is very interesting in a sense which I will mention later. So A circle B, if you define B dot A, then you can check that okay. So then it becomes a skew left brace. And so the point is that, yeah, there are many more examples. And so the point is that there's a question how to construct more skew braces from groups. And so this theorem is a recipe for constructing skew braces from groups. So let me read it for you. So start with a group and an anti-homomorphism from G to out G, such that these elements A lambda A B, A inverse B inverse is in kernel of lambda. I'm sorry, I did not actually define for you. No, just sorry, lambda is here. This is given to us. So lambda is a anti-homomorphism. So what do really lambda A means? You take an element A, then the image of A under lambda is denoted by lambda. That was the confusion. This lambda A is the image of element of A in G under lambda. And if these elements are all A, B, and G are in the kernel of lambda, then you can define a skew left brace, where circle operation is given by this. So A, so this operation here is dot, which is given in the original group. A dot lambda A for all A, B, and G. If you define this, then you're really going to get a skew left brace. And so the beauty of this skew brace is that in this skew left brace, you can interchange your operations, dot and circle, and still you get a skew brace. So that is called a symmetric skew brace or a bi skew brace. So Krishnenduji, could you please warn me about the time? Otherwise, I will keep going.
Yeah, I think he is not here.
Okay, no problem. So I suppose I will still have 10 more minutes. Maybe between 5 and 10 anyway. So, so if you start with a skew brace, then you can define a map lambda AB like this. So A inverse dot A circle B. This is always an automorphism of G dot, and the map which takes A to lambda A from G circle to G dot is a group homomorphism. So this is actually a very, very fundamental object in the theory of skew braces, even in the theory of braces. So I forgot to mention that if you take your Reddit set to be involutive, then AX really comes out to ZX. So this is an abelian group. And so what we really get is a brace, left brace or right brace, whatever we get there. So whenever this additive group, so means that if the group G dot is abelian, then we call it a left brace. So that's the terminology. And so if you are given a skew brace, then you can categorize it into some categories like, so this lambda is actually going to be a map from G dot to or G dot, because the underlying set is the same. So you can view it as a map, but this map may not be a homomorphism from G dot to or G dot. If it is a homomorphism, then we call it a lambda homomorphic skew brace. If it is an anti-homomorphism, we call it a lambda anti-homomorphic skew brace. And so the lambda anti-homomorphic skew braces are actually in some connection with the symmetric braces. I do not have much time to tell you all these stories, but let me continue to show you how to construct more and more skew braces. So let me define for you the brace system. The brace system is, I am not giving a formal definition because what we have defined is using some graphs. But here, to make it simple, I just say that take a set G and certain operations on binary operations on G, circle I. We call this system a brace system. If whenever you take the circle I, circle J, I less than or equal to J, this is a skew brace. So, notice, try to visualize it. The set is the same. There are lots of binary operations, and we claim that whatever circle I, circle J you take, we take the partially ordered set. So whenever I less than or equal to J, this we want it to skew brace. So this is a brace system. We call it symmetric brace system if you don't bother about the ordering. So whatever circle I, circle J you take, you always get a skew brace. So these are actually, all these braces are going to be symmetric skew braces because you're allowed to invert I and G. So let us see how to construct. So you start with a lambda homomorphic skew brace with the image of lambda G circle 1, an abelian subgroup of odd G circle dot. So because I want to introduce more suffixes for the circle, so I start with 0 and 1. So you can take this circle 0 to, so this one is because it's a skew brace, so we know that there is a homomorphism, this one, G circle 1 to or G circle 0. But because it's a lambda homomorphic skew brace, so this lambda, the same lambda, is also a homomorphism. Then one can check that in this particular case, all these automorphisms which land in automorphisms of G circle 0, there are also the automorphisms of the group under circle 1. And also the property, this property is satisfied, B inverse circle 1 lambda AB in the kernel of lambda. And so the condition which I showed you was a little more complicated, but if you come to the homomorphic skew brace, lambda homomorphic skew brace, then the condition actually turns out a simpler one. And so you can check that this condition is satisfied here. And so by the theorem, you can construct another operation, which is circle 2 in this fashion. And then you can keep going. Every time you repeat this procedure, and I always get a homomorphism, and then repeat that theorem again. And so you can keep going, define these circles. And so it now depends on the exponent of the image of lambda in the odd G circle 0. If it is finite, you will get finite ones. If it is not finite, it will keep going. But you cannot guarantee that all of these skew braces are non-isomorphic. But so that we don't know. But I'm now going to present an example where we can always get non-isomorphic stuff by this procedure. So I will quickly finish. I suppose my time is almost over, but I quickly tell you the story on this free group. So this free group on n lattice, take theta, which is an inner automorphism by a fixed element omega or w, non-trivial element in Fn, and define this map xi to theta. So that on the basis you xi goes to theta. So accordingly, this extends to a homomorphism from Fn to order theta. So image of lambda is now a subgroup generated by theta, subgroup of the automorphisms of Fn, which is certainly cyclic, so abelian. So this fits in our setting, and also the condition that condition which we want, the B inverse lambda AB is in the kernel, will be satisfied here, because more or less we are going to get these elements are actually the kind of elements of this type. This particular element is in gamma to Fn, and because the image is an abelian group, so lambda will map these elements to the identity. So this scene is set now, and so all the conditions are satisfied. So you can define another operation. So from this free group, you can define another operation, circle 1, in this fashion. So this becomes a skew brace. And the interesting thing is that this skew brace comes out to be the same direct product of the F infinity, and that's the free group on infinitely many elements. And so this is the action, and so F infinity is given like that, generated by these kind of elements, and the action is here. So that's the action. So there's a mystery here. So when you take this action, then some M comes into the picture, and this M is not actually, it's very nice, and so this M satisfies this condition. So the omega is congruent to x1 to the power m modulo kernel of lambda. And this is very important in the sense that we can always find an M for a given omega. So that's what I have explained it here. So W, you start with any omega, you can take M to be the minus of the sums of all these powers occurring, and then omega is really going to be like that. And so this is an extra information that any element whose the sum is going to be 0 is in the kernel of the lambda map. And so if M is not equal to -1, then it turns out that this is a finite, a free group of finite rank, and these are the generators, and the rank of Fn circle 1 is given by this method. When M is equal to -1, then we really get that this operation, this semi-direct product actually becomes a direct product, and so it is infinitely generated group. But if M is not equal to -1, then we really get a free group of finite rank. And so my motive here is to tell you that when you can define circle 1, then you can define circle 2, circle 3, and so on. You can also define a circle on the minus side. And so every time the rank of the free group increases. And so there is no danger that they will be isomorphic. So in this case, we always get infinitely many non-isomorphic skew brace, and we really get a system, symmetric brace system. All right, so what is the connection on the other side? I have said that if there is a braided, non-degenerate braided set, we can define a skew brace. On the other hand, if you have a skew brace, then you can always define a braided set, non-degenerate braided set by using the lambda map. As I said, lambda is a very fundamental object in skew brace theory. So as AB, lambda AB, if you define like that, then this turns out to be a non-degenerate braided set. And I'm done. Thank you very much.
Krishnendu. I think he is not here. Okay, so I think let me take charge. Let us
Yeah,
thank
please.
Dr. Manoj for a wonderful talk. Any questions or comments?
I have a question.
Yeah, please go ahead.
Could you say if the extensions of Skew Braces that you constructed can be controlled by some cohomology theory?
Yeah, that is a different story. There is a theory of extensions of skew braces and a second cohomology, and there is a correspondence. So that has been developed.
But what kind of second cohomology?
This is the ordinary one using the ordinary two cocycles.
Okay.
Analogous to the cohomology theory in groups. Actually, I'm not an expert on cohomology. I know there are so many cohomologies, but I only know the one cohomology, that's the ordinary one.
Okay. Thank you.
Okay, so may I ask some question?
Yeah, please.
Yeah, so I think maybe Professor Talalev asked a question, if I understood, that you have given a skew brace, you have constructed a family of skew braces, whether all these skew braces can be parameterized by a cohomology. Perhaps, I mean, you have constructed a system, right? So
this is only a particular example in which it really comes out to be the semi-direct product. Not always.
Semi-direct product of what?
No, in this case, when I started with this free group FN, and in this particular setting, when I take this theta to be the inner automorphism, in this case, the next one, next operation, circle one, and the group under the circle one comes out to be the semi-direct product of infinitely generated free group by Z, the cyclic group.
So if I understand, could you please go 2 slides back?
Yes.
Your definition of brace system or semi is like you have the underlying set is the same, right?
Yes, yes.
But then when you gave this example of free group, you are saying that it's a brace system and the ranks are increasing. So I was a little lost there.
Okay, so this one is the example.
Yeah, so here the ranks are increasing. So how you are calling it a brace system?
Ranks are increasing, but the set is the same.
So underlying set, what is the underlying set here?
Underlying set is the free group on n letters.
N letters and okay.
So
And then on this free group on n letter, you are
yeah, as I said, we define another operation which is circle one by this definition. So this really comes out to be a group, and that group is this group.
okay.
Because free groups can have subgroups which are of infinite element.
Yeah, of course. But your set is fixed, right? So I was little
Yes.
Okay.
So the set is just a countably infinite set. Yeah, right. And then you're considering free group on n letters.
So this one is what it is. The started with whatever it is, and then the same set is.
Yeah, okay.
So, and then can I see the 2 slides? The last slide where you constructed the brace system. So is there any way? So there you started with a skew brace, right? And then you constructed a family of.
In this case, I have started with just a group.
No. The main theorem. This was, I think, an example.
Yeah, this one.
Yeah. So here you started with a skew brace. So can we impose some conditions on this skew brace or the underlying group structure so that we know, okay, that whether this family will stabilize at certain points or some way to parameterize isomorphism classes of skew braces arising from this given one?
Unfortunately, we have no mechanism to check that. We got a small result which is in our paper, but that is, I'm not sure that will do the job.
Okay, thank you. Any more questions or comments? Okay.
Okay, so
Martinder, can I say maybe on your question? Because see, this is new construction. Before we know only the definition of skew brace, but now we introduced so-called brace system where we have not two operations, but a set of different type of operations. And idea was the following: we are consider the free group of rank and is it possible to define new operation such that the group with this operation it's not free of rank n, and we constructed a lot of different groups with infinite number of operations, and the rank of these groups are different, hence these groups are not isomorphic. This is the main idea of this part. Is it correct, Manoj?
Yes, you're right. Yes.
Thank you.
Yeah, but there is something that in the free group that made it that made the rank go higher and higher up. So my question was, can some condition be imposed to on the starting skew brace, the circle 0 and circle 1, where we have some control on the number of operations you are able to cook, not isomorphism classes of, yeah.
This is an open problem, I suppose.
No, see, I think that we are used the idea from our first paper. The first paper is so-called lambda homomorphic skew brace, because when Manoj explained the map lambda, it's not in general case a homomorphism, hence it's difficult to construct new examples of braces. And we, not braids, skew braces. And it's difficult to control these maps. And we introduced the so-called lambda skew braces, where lambda is a homomorphism, in which case it's possible to control a new operation and construct some new examples of braces, skew braces, and so on. I don't remember which brace we take at the beginning. I think some standard skew brace. And using this operation, we construct infinite number of operations.
Yeah, okay. Thank you.
It's possible to start with a lambda homomorphic skew brace or start with a group with the favorable conditions. So in this case, we just start with the circle 0 and circle 1 in hand, but we can also start with just circle 0 and the conditions, favorable conditions that can define circle.
Yeah, those conditions are equivalent to defining the other circles so that together they form a skew brace.
And the conditions also make sure that at each step the conditions are really going to be satisfied repeatedly.
Okay.
That is the beauty of the construction.
Yeah. Somehow these constructions look something like Postnik or tower in algebraic topology. I don't know whether there is some relation. Some analogy coverings or something like this.
It will be great to find connections.
Okay, thank you.
okay. So thanks, Manoj, for this talk, and thanks everyone. So that's the end of the.
Thank you, Manoj. Please say hello to your wife and sons.
Thank you, Larry.
Okay, thank you.
Hoping to see you soon in near future.
Oh, okay. I also hope.
Okay. So we meet in the afternoon.
Easy.